Cool. Now I'll share my screen. Okay. So today I'm presenting this paper / chapter of this book called MCMC using, which is Markov chain Monte Carlo using Hamiltonian dynamics. And it's abbreviated in the paper as HMC, and I use that further down, which is why I have HMC here. Before I even start the presentation, I just wanted to go take like a quick step back to like why this is important, why we're talking about this. So MCMC is a method that you see used in a lot of different places. And the reason why it's used is because it's a method for sampling from a probability distribution when you don't fully know the probability distribution. And that might sound pretty niche, but it actually ends up being something that happens quite a bit when you're like, especially when you're trying to combine like different distributions that look very different from each other. And you want to know like what their maybe like what the joint distribution is or what the resulting distribution is from taking an expectation. There's a lot of different times when it can be quite difficult. And what that means is that MCMC can be used, I think, probably in more situations, but these are the two I picked to highlight, which is if you were doing like a sampling-based optimization method where you had this issue, you could still use MCMC to actually still use that sampling-based optimization method. And sampling-based optimization methods, I think, are not something we see that often, but I actually think they're quite useful. It's just that they're not in vogue right now because everything has to be differentiable, and they're looking at anyway. Another reason why you might do it is just so you can characterize the distribution that you're trying to and using samples like that you're trying to understand. So maybe you have like different distributions for different assets in a portfolio, and you want to know what the overall distribution of value of the portfolio could be. Then you could just use this method in order to like combine all of these to get like the value of the overall portfolio. Also, as a reminder of why we're even talking about this, I chose to look into this topic because one phrase that I've seen every so often in deep learning literature is longevity dynamics, and I didn't know what it meant, and so I wanted to do like a deep dive to understand it. And we actually read a paper a while back where we looked at how they posed the end of the learning process of a model as longevity dynamics with using for MCMC, so that you could get like multiple different versions of that model based on the data. So you also see this stuff popping up in deep learning literature every so often. So it's not just like an old technique that's never used. It's still something that's part of active research in like the main field of machine learning right now. Okay, let's go to the next slide. Okay, so what am I going to present in this presentation? A brief history of the Hamiltonian and Metropolis algorithm, or a review of Markov chains, because yeah, I think that will really help kind of ground the whole discussion. How does the Metropolis Hastings algorithm meet the detailed balance condition? I'm revealing, I haven't told you guys what the detailed balance condition is yet, but that's like, if there was like a heart to all of this stuff, it's the detailed balance condition. So we'll get to that. Then an introduction to the Hamiltonian, and then how is the Hamiltonian applied to MCMC? And lastly, how does Hamiltonian Monte Carlo algorithm meet detailed balance as well? We have a lot to cover. We'll see how much we get through. And then I'll just say this. I am not going to cover, I'm doing a review of Markov chains, but I think that every time we present this topic, we have to do a review of Markov chains. But this time this time and next time I'm doing a review of Markov chains, but this time I am not going to be talking about like why would you use the Hamiltonian Monte Carlo instead of the Metropolis Hastings algorithm? I'm not even going to be talking about longevity dynamics yet, and like why you would use longevity dynamics versus HMC or the Metropolis Hastings algorithm. All of these are algorithms to perform Markov chain Monte Carlo. So this one is more, this presentation, what I'm hoping for you to get out of it is like why you can apply the Hamiltonian to MCMC. Like why does it even work? The next presentations will be like, why is it often better than just doing the standard MCMC? Or like, when is it better? And that's one of the reasons why you would use longevity dynamics, which is a form of this like Hamiltonian approach to MCMC. But before I do any of that, here are the three resources that I used when I was creating this presentation. This is the paper. This is like a PDF that has a really good explanation of some of the theory behind Markov chains and stationary distributions. And then this is a really good YouTube video on the Metropolis Hastings algorithm. Okay, so let's do the brief history of the Hamiltonian and the Metropolis algorithm. So again, both of these are used for MCMC right now, but they actually didn't start that way. And I find it interesting that they were both created to address basically the same problem. So the Metropolis algorithm, which by the way, the reason why it's called the Metropolis algorithm is because it was written, the first author on this paper is Nicholas Metropolis. I actually thought it had something to do with like the Manhattan Project, and that's why they called it that, but it's the last name of the author. So the Metropolis algorithm was published in this paper in 1953, and it was a way of simulating the distribution of states for a system of idealized molecules. Whereas, and the thing about it, I'll get to that. And then the Hamiltonian was published about 6 years later, different authors, and it was for the same problem. And the interesting thing about it is the Metropolis algorithm is a stochastic approach, whereas the Hamiltonian is a deterministic approach. So like the Hamiltonian is based on equations, in its raw form, there's literally no sampling that goes on. So there's no randomness in the Hamiltonian, but it still is really good at simulating like these idealized states of molecules, of these states of idealized molecules. So I thought that was interesting, but I also find it interesting that like the Hamiltonian is a deterministic model, but we can use it to approach this sampling problem of MCMC. Just thought that's interesting. But yeah, they both come from the same problem, and then which maybe isn't too surprising, and then we found a way to apply it to like a large number of statistical problems, but both come from physics. Oh yeah. So the Metropolis algorithm was produced in 1953, but it wasn't until 1970 that like the Metropolis Hastings algorithm was created, and that's like the more popular one to use. And it was in the 1980s that all of these algorithms started to be used in statistical applications like MCMC. Okay, so let's do a quick review of Markov chains, or maybe not super quick, but anyway. This is like a very basic diagram of the conditional dependencies in a Markov chain. So every state is dependent on the state before it, and if you have knowledge of the current state, then you don't need knowledge of the prior states in order to it doesn't provide any additional information to know about the prior states if you know the current state, about what the future states of the system will be. That's why there's like, basically you could think of each of these time steps or these states at these time steps as like a wall that separates the past from the future. And that's like a key idea in Markov chains. So this is showing the conditional dependencies in a Markov chain, but we also have to think about it in terms of its state space. So here's a really basic state space, which is like a grid. So at each time step here, like xt, the system could be in any of these states, 1, 2, 1, 1, 1, 0. And so we have to remember that there's like a set of states that are achievable with that you may be in when you're travel, like when you're progressing through a Markov chain. And related to states and both like the time series, which is a Markov chain, and the states, there's this idea of a stationary distribution. And the stationary distribution is a distribution where the frequency of states in the series remains constant over time. So when you start doing, when you start sampling from a Markov chain, you're not necessarily in the stationary distribution. But over time, if you have the right conditions, you could converge to the Markov chain stationary distribution. And that's when like there will be a frequency at which every state in the Markov chain it is like visited. So maybe like 1 every 100 steps or 1 every 20 steps. And from that point onwards, when you've reached that stationary, when you converge to the stationary distribution, you should consistently see states appearing with a specific frequency, and it shouldn't change over time. And this is a really key idea for MCMC, because the whole idea of MCMC is that we make a Markov chain whose stationary distribution is the distribution that we want to sample from. And then we can use this Markov chain's properties to generate samples by just progressing the Markov chain forward. So like by transitioning from the current state to the next. And so here's a lot of the math that I'm gonna show you guys is for a discrete Markov, like a Markov chain with like a finite number of states. I think that the math that I'm showing you translates pretty easily to continuous. But if anyone doesn't think that's the case, please correct me. But here's like an equation which describes a stationary distribution of a Markov chain. So P is the transition matrix of this Markov chain, which means that say you're in state A, that would be one of the rows in your transition matrix, and it would have a value for your likelihood of getting to any other state, like a probability of transitioning to any other state in your state space. So maybe you only have B, and there's like a 50% chance you stay in A and a 50% chance you stay in B. Then that would be the row in your transition matrix. And then you have your stationary distribution, which is a vector, which gives a probability, like the frequency that you're going to be in that state. So maybe it would be like half of the time you're in A and half of the time you're in B. And basically what a stationary distribution means is you can multiply the stationary distribution by the transition matrix, and it returns the stationary distribution. If anyone's familiar with linear algebra, and I'm going to go into a little bit of linear algebra, which I hope isn't too too much, but this equation might remind you of eigenvectors and eigenvalues, because this is really similar to how you would describe an eigenvector and an eigenvalue. The only difference is there's a constant here, which would be the eigenvalue. And the reason why what that should tell you, and we'll touch upon this later, is that a stationary distribution is a eigenvector of the transition matrix, and its eigenvalue is equal to 1. We'll go into later why that's important, but I'm just bringing that up now. I also had some notes. I just want to make sure that I want to make sure that I didn't. Yeah. I'm glad I looked at my notes. I'm not sure. So another thing about this, and is that in order for this to be true, that the stationary distribution pi equals the stationary distribution times the transition matrix, that means that the flow of probability out of any state by the transition matrix has to equal the flow of probability in any state. So for example, maybe like A has a probability of 0.5, and when you multiply it by the transition matrix, 0.3 of that goes to state C. That means that 0.3 has to come from some other state or other set of states into A. I find that as a useful way of thinking about this, which is that like like this condition is about like the flow of probability as you transition through the Markov chain. And as I said before, with the stationary distribution, the flow of probability out of the state has to equal the flow in. Don't use that in a proof, but I think it's a good intuitive way of thinking of it. Okay, so here's another equation which is equivalent to the one above, but you're going to see this notation a bit, so I wanted to explain it. So like S is your state space, I is like a state in your state space, and a stationary distribution is one where like P Ji is like you're multiplying you're multiplying the stationary distribution by a column. So it's like saying that Pi is equal to multiplying the stationary distribution by i's column, and you get Pi back. These are pretty similar. I hope this notation makes some sense or is easy to go through. Okay, so we've reviewed stationary distributions, and then what's the sufficient condition for a Markov chain to converge to its stationary distribution? This isn't like there's other ways that a Markov chain can converge. Like there's other conditions, sufficient conditions for a Markov chain to converge to its stationary distribution. This isn't the only one. There's other, like there's Markov chains that converge to their stationary distribution that don't meet the detailed balance condition. But the detailed balance condition is what is used to make MCMC methods work. If you can prove that your MCMC method meets the detailed balance condition, then you know that it's going to converge to the stationary distribution. Yeah. So what is the detailed balance condition? This, and like I said before, this is like at the heart of MCMC, at least everything I've seen so far. I'm sure that there's extension. Actually, I think in the paper they even mentioned there's extensions where you don't have to meet it. But anyway, this is at the heart of all of the theory that that is related to MCMC. And it's the condition that, like, I guess this isn't the greatest, but anyway, it's a condition that if your probability of being in one state, pi I, times the probability that you'll transition from I to J, should be equal to be the probability of you being in state J times the probability that you'll go from state J to I. So basically it's saying that the likelihood of you going from I to J has to be equal to the likelihood of you, the likelihood of you being in J and going to I has to be the same as the likelihood of you being in I and going to J. I hope I said that correctly. Yeah?
So that's for clarification. So this is a more strict assumption than just stationarity, right? Stationarity, that doesn't have to be true, right? You could go, I don't know, in a 3-state circle and you would be stationary, but you wouldn't be detailed balance according to this equation.
Yep, that's exactly true. This is a stronger condition because remember how I said for a stationary distribution, the flow of probability out of the distribution has to be equal to the flow in. That could be like the flow out could be to states A, B, and C, and the flow in could be from states E, F, J. So they don't have to be exactly the same. But here what this is saying is that if you are giving, if the transition matrix gives 0.3 of your probability to state B from A, then B has to give 0.3 back.
Yep. There's
no net flow between states of probability based on the detailed balance condition.
Gotcha, thank you.
Yeah. Oh, and so if you can prove that, I'm not going to prove this, but or talk about why it's true. But, if you can prove that the detailed balance condition is true for some distribution, that distribution is the Markov chain's stationary distribution, and it's unique. So it's the Markov chain's unique stationary distribution. That's some result, which I actually didn't even look into the proof into. So first off, there's 2 questions here that I wanted to answer. The first is, actually, no, yeah, here's the proof for it. The first is, if Markov chain meets the detailed balance condition, then like, why is this distribution for which it meets it, pi, the stationary distribution? And that's really simple. So if you remember up here, this description, this is one description of what makes a distribution stationary. This is the same description, but with like notation, subscripts to indicate like positions in a vector and matrix. And so if you take these values and then you apply the detailed balance condition, you can see from like going left to right from step 1 to step 2, you're switching pi I with pi j, and then flipping the probability, like the value in the transition matrix, the subscripts in the transition matrix. That's literally the detailed balance condition, as you can see it up here. So if you flip it, then what you can do is you can say this is equal to pi j, and then because you know that this is a probability distribution, that means that like this column should sum to 1. So this is equal to pi j. So you by just using that equation, you've shown that like there's a stationary, that this is a stationary distribution. Pi is a stationary distribution of the Markov chain. Because you're able to use, like going from here to here. Can you see my cursor? Yeah, going from here to here. You're using the detailed balance condition, and what drops out is like this definition of stationary distribution. Yep. Okay. And now I want to give like an oversimplified explanation of why it converges to the stationary distribution, because I've shown you that like if a Markov chain meets the detailed balance condition, that like it has a stationary distribution, which is the distribution that meets the detailed balance condition. But I haven't shown you why, starting from anywhere, starting from any state, how your model will initially converge to the stationary distribution. And again, I'm giving a very simplified explanation, which isn't completely correct. Actually, I think it's like 50% correct, but the intuition of it is correct. So that's what I'm hoping you'll take from it. So here's the third equation or fifth equation you learn when you take a linear algebra class, which is related to eigenvectors and eigenvalues. So you have your some matrix times a vector is equal to a scalar factor times that vector. And so lambda is the eigenvalue, and v is the eigenvector. Yeah. Now, and one way to think of eigenvalues and eigenvectors are like, depending on the matrix, let's just say this is true, the eigenvectors form a basis for that matrix, which means that you could take any vector and describe it as linear components of that that basis. I'll give a really simple example here, which if you can see, I want to highlight it. So here's a basis. This is one eigenvector, and this is another. It's the one that we actually always use when we're plotting stuff. You can see that you can see that like any number, like I could give any random vector, say like 0.47, and then 1.2, and then you could rewrite this as equal to like 0.47 times 1, 0, 1, 0 plus 1.2 times 0, 1, just as an example. So the so really simply, like in the right conditions, the eigenvectors are a basis of the mapping that of the matrix, and the eigenvalues are how much like each of those directions is scaled. So and usually and in the cases that we're talking about here with like the types of matrices that we're talking about here, the eigenvectors are are normalized, so they have a magnitude of 1. and so here's an example of for a transition matrix with some that meets the I don't know if it meets the detailed balance condition, but like again, this could be the eigenvectors and eigenvalues of a so the eigenvalues would be 1 and 0.5, and the eigenvectors would be this and this of transition matrix for a Markov chain. And every time you multiply, and then say you start at point, like say this is 1, 1, every time you transition using that matrix, basically what's going to happen is the component of your vector that's of like one vector, like one of the basis vectors. So in this case, 0, 1 is going to be multiplied by 1, and then the other one is going to be multiplied by 0.5, and they're going to stay the same otherwise. So that wasn't a great explanation, but let's just like the overall thing I want to show you to notice is that like this eigenvalue is 1 and this is 0.5, which means that as you transition over and over again, your point is going to move closer and closer to the eigenvector with the largest eigenvalue. And in this isn't completely true, but this is how I think you should think of it. In like really simplified terms, what's going on when you meet the detailed balance condition is that you could think that your stationary distribution is your eigenvector that has the largest eigenvalue. And as you transition, you just converge to it, even though you could start from anywhere, because it doesn't matter, because what's basically happening is like everything else is becoming smaller, while like all the other, the likelihood of any other state is becoming smaller, while the likelihood of like you go ahead, Arvid.
Yeah. I remember, I think the other eigenvectors, they have to be summing up to 0, I think. Just because you have this very strict conservation of probability mass, right?
Mm.
And so what you have already some eigenvector plus something that is this, at best is a perturbation, so that sums up to 0, right?
Mm.
I think you can very convincingly argue that you can't have positive eigenvalues, otherwise your system would essentially keep oscillating and get bigger amplitudes, and eventually that must break your conservation of any probability, right? There's going to be one state that has too much value in it, and so that can't be. So that can at best be negative real eigenvalues. You could still oscillate, yeah, and so then over time those must dampen out essentially, because they sum up to 0 and their overall magnitude goes down.
Yeah.
Plus they are important because it's sort of the second largest tells you essentially how quickly your system converges to stationary state, which of course is quite important in a lot of these problems.
Yeah, and that's actually what we're going to be talking about in hopefully less detail, or like not as complicated math next time. But yeah, I like that explanation. Thanks, Arvid. The overall idea is I'm hoping you get is like through this picture, it's just that no matter where this vector was, it's just pushing this line every time you transition closer to here. That's like a really simplified version of what's going on when you meet the detailed balance condition. And that's why it converges, because it doesn't matter where you start, because it's just always moving closer and closer to that, like the stationary distribution, which is the eigenvector with the largest eigenvalue. Okay. So, and just to hammer it, this condition is what is used in MCMC. This is everything. So how does the Metropolis-Hastings algorithm is kind of the OG algorithm. It's actually the Metropolis algorithm, but what's like the Metropolis-Hastings algorithm is the OG algorithm for MCMC. And I want to go over like how it meets the detailed balance condition, just so you can see that. So you start out with some function f of x, which is non-negative, and it's your that's your unnormalized probability distribution. So that's what you want to sample from, but you don't know how to normalize it. And then G is some probability distribution that you're using to sample new candidate values for your Markov chain. The main constraint of G, I think, is just that the mean of the distribution has to be the previous state's value. So what you do is and these are the steps that you do. You start from some initial state x naught, then you sample from G to get x, or I call like 1 under comma t. And with acceptance probability a naught, you either accept x1 comma t as x1, or you use x0 as x1. So these are the steps, and you just continuously do that. So once you get x1, you just do steps 1 through 3 as if x0 is x1. So it's like sample a new state and then accept it with some probability. And the way that we enforce the detailed balance condition by choosing, oh, this is my bad, the right acceptance probability. So we actually chose, like, the acceptance probability that's used is chosen based on meeting the detailed balance condition. Now here's some math that I hope is, or some algebra, which that I hope isn't too much. So how does the Metropolis Hastings meet detailed balance? So here's like an equation which describes the detailed balance condition. If we go back to, where is it? Here. This is one, remember this, I'm just going to copy this so we have it while we're talking about. So pi in this case is 1 over z times f times f. And then your transition probability from I to j is g times your acceptance probability. So g is how you get your new state, you sample from that, but then you also have to choose whether to accept it or not. And so your acceptance probability and g are your likelihood of transitioning from x naught to 1. And what you need to happen is you need these two things to be equal to meet the detailed balance condition. So next step is I'm just rearranging the equation. Now you have the acceptance probability of going from x naught to x1 divided by the acceptance probability of going from x1 to x naught is equal to these two fractions. So f is the distribution that we want to sample from, is like the unnormalized function for the distribution we want to sample from, is g is the distribution that we chose for sampling. We can do some substitution. So let's say rf is equal to this fraction, and then rg is equal to this fraction. And then we can just notice that the acceptance probability fraction is equal to rf times rg. So we have two cases for the ratio of the acceptance probabilities. One is that the ratio is less than or equal to 1, or it's that the ratio is greater than 1, because it's a number. It has to be one of those two things. So if the ratio is less than or equal to 1, then you let the acceptance probability of a naught going to x1, x naught going to x1 be rf times rg. And you let the acceptance probability of going from x1 to x naught be 1. And then if the ratio is greater than 1, then you let the probability be x naught times x going to x1 being 1, and this one being 1 over rf times rg. And not now, but if you do the math, you see that when you set these acceptance probabilities this way, this equation is always true, which means detailed balance is always held. It's always met, sorry. And what that means is that that's how we choose the acceptance probability. This is the way that you choose the acceptance probability for Metropolis Hastings. And by choosing it this way, you know you've met detailed balance, where it's it's either 1 or RF times IG. So yeah, that's one example of meeting the detailed balance condition. Now let's talk about the Hamiltonian. Hope you guys found that interesting.
So one quick question, if I may.
Yeah.
The RF. So F was the distribution density, right, of the states.
Unnormalized density.
Yeah. And this is something you know, or I would have thought that is the thing you sort of try to find out.
You don't know the density. So you don't know the density because it's unnormalized. What you don't know is the normalization constant, but you do know like the unnormalized likelihood.
Okay, I see.
So if there's some number that if you divided everything in F by would make it a probability density function, but you don't know how to perform that integral to get what that number is.
Okay. So just knowing the transitions is not enough.
Yeah, not enough.
Gotcha. Thank you.
Okay, so let's talk about the Hamiltonian. So the Hamiltonian is, as we talked about before, something that comes from physics. And it's composed of a couple of different things. So you have a d-dimensional position vector that's Q. I don't know, I'm using the notation they used in the paper, but actually it was like, why didn't they use P as a position variable? Anyway, I think this might be like standards in physics, though. That's why it's done that way. So Q is a d-dimensional position vector, and P is a d-dimensional momentum vector of a system. And the Hamiltonian, the way they describe it in the paper is, it's like a system where you have a puck that's moving around on a surface that has a varying height. I chose a point mass, which I don't think is wrong to say that it could be just a point mass moving around. And so what the Hamiltonian is it's a combination of U, the system or the point mass's potential energy, which changes as it changes in height, and its kinetic energy, which changes like as it loses energy to potential energy, because the sum of these two is a Hamiltonian, which is constant. So that's the basic idea of the Hamiltonian. It's a system that describes the system is described through an energy equation, and it's about like points moving around on a surface. And these are the transition equations for the Hamiltonian. So this is how the system evolves over time. What you can see is that like the change in position over time is equal to the derivative of the Hamiltonian with respect to P, and the change in momentum over time is equal to minus the change in the Hamiltonian with respect to Q. Yeah.
Yeah, sorry to butt in here, but it might be quite interesting. I mean, this is exactly like your energy equation, as you said. What makes it sort of special is that you have a first order equation of time, right? So if you think back to your Newton physics, typically you have second order derivative in there, and by reformulating it like this, you get rid of the second order. So your momentum becomes to some extent a regular variable like your position, which is why these are so relatively symmetric. I mean, there's a sign and everything, but apart from that, momentum and position are sort of the same, can be treated on the same footing, and that makes it quite powerful, because you don't have to be actual positions. They can be what's called generalized positions, like a particle on a circle, for example, can still be described by this equation, even though Newton would probably break down if you're not very careful.
Yeah, that's a really good point. And actually, probably like that's an intuition that I didn't even think of. But now that you mention it, like when I took a class on ordinary differential equations, like I think I remember learning that trick.
Yeah.
Is that trick called the Hamiltonian, or is it just?
I think that was it's true, right? You can sort of put every Markov system that they have like some sort of history of momentum into just defining your variables or your momentum as variables that you then treat as yet other variables, so that you can always sort of press it into this format and technically have solvable equation. In practice, they can be incredibly hard to solve, but in principle, I think this reasonable assumption of continuity and whatnot, where mathematicians go nuts.
Cool, thanks. Okay, so this is the system. Again, it's a physical system for describing how an object changes its position and momentum over time. And so the Hamiltonian has some important properties. One is time invariance, which is that, like, for any time interval s, the equation in the previous slide defines a mapping Ts from the state at time t to the state at time t plus s. So these equations, they define how the system changes over time. And the point that it's saying here is basically, like, doesn't matter if you're starting at time 1 or time 5. These equations are always true. They don't change. And if you're moving by 1 second at time 1 versus time 5, you'll have the same transitions that occur. Not that you'll, it depends where you are in your state that determines how you change, but it doesn't change with respect to time. And so it's time invariant, which is kind of, I think that's how that is needed to enforce a Markov property, which is that you only need to know your current state in order to know your future states, or past states don't provide any additional information. So the second property of the Hamiltonian, besides that it's time invariant, is that it's reversible. So Hamiltonian dynamics is reversible. The mapping Ts from the state t, from the state at time t to the state at time t plus s is 1-to-1, and hence the inverse of t minus s. This inverse mapping is obtained by simply negating the time derivatives. I'll actually show you a diagram that I created that shows you, in the examples that we're going to look at later, this is completely true. So say that you're at your point Q naught and point P naught, Q naught, P naught, you're at this point. And you do your mapping TS. So this is taking you 5 seconds in the future. And then you have this new point Q1, P1. If you just negate the momentum variable, so you multiply it by -1, and you apply the same mapping, you'll get back to Q naught, P naught. So that shows how this is reversible. How you can go from where you were exactly back to where you were before. So it's reversible. Excuse me. And the last point is that the Hamiltonian is conserved. So the Hamiltonian does not change with respect to time. It does change depending on what position you're in, or does it? No, it doesn't change with respect to time. We'll go with that. Okay, there's that. And then volume preservation. A third fundamental property of the Hamiltonian dynamics is that it preserves volume in QP space. If we apply the mapping TS to the points in some region R of QP with volume V, basically the Hamiltonian, when you use it to propagate forward in space, it will change the values of these positions, but it won't change the overall volume between points if you were to start at different positions. It's a bit of a tricky one. Yeah, go ahead, Arvid.
Sorry, I hope it's not too annoying. But
no, it's not. It's very helpful.
This is actually really an interesting one, right? Because what it essentially means is that you just said you can reverse everything. So if I have a probability distribution at any point in time, I can move it forward and backward again. And what this Liouville theorem in particular means is that the entropy, if you have a system where you have like uncertainty about, that the entropy can never increase. It always is going to be exactly the same, because every tiny bit of probability is sort of conserved, right? It can't go anywhere. So the total entropy space is actually also the same.
Mm-hmm.
Which is slightly different from when you think of your transition matrices, right? The transition matrices, you apply them over and over again. You can start with a state that has a 1 in one state and 0 everywhere. So it's 0 entropy. And if you keep going, your maximum entropy state is your stationary distribution, right? So you actually have entropy increasing. So there is this connection between lossiness in some sense, where if your transition becomes lossy, you increase entropy, whereas if you technically that is not the case, right? Because in nature, like everything moves along these Hamiltonian lines, so that sort of means that entropy increase typically is something that is correlated to loss of information.
Hmm.
Yeah.
Well, it's exactly that, right?
Yeah, pretty much, and it's subjective, right? So you could, in principle, have two people see the same system, have different entropies assigned to them, and therefore entropy is like the information entropy is something human-based rather than natural. But the maximum entropy a system can have is then something that is natural.
Hmm. It's interesting that you say. I never thought about that like volume of a probability distribution is related to its entropy. I'm definitely gonna have to think about that so I can understand it a little bit.
Yeah, but at least in a continuous space, I think. So if you imagine you have a single dot, it's like your delta distribution, right? So that it has no spatial extent whatsoever.
Mm-hmm.
After moving through the Hamiltonian, it still will be exactly the same dot. It won't have spread out by itself because of that reversibility.
Mm-hmm.
Yeah.
Yeah, that part makes sense. Well, I was thinking you could have something reversible that changes in volume, though, right?
Well, it would be. I don't think so. I think the.
Yeah, I guess because maybe there's many ways to get to that point when you start changing the volume.
Yes, it's let me think, but I think it has to start already with a volume in order to go there.
Mm.
It's this weird thing. I don't know whether you've ever seen this. I might have even showed it in one of these lectures. When you have a very, very viscous liquid and you put a drop of paint in and you rotate it, it looks like it's smearing out, but you can actually rotate it back and it almost perfectly comes back. So while it is very, very thinly spread out,
Mm-hmm.
the total volume would still be the same. It won't be dispersed per se.
Mm.
Yeah.
Cool.
Sorry, that was me.
Okay. I'm cognizant of time, so I'm going to rush a little bit through the last parts of it. So far, we've talked about the Hamiltonian and what the equations are for it and some properties of it. These are the equations. But you have to take these equations if you want to know like how a system is going to propagate and propagate, use them to propagate the system through time. So you start at some position in momentum and you move through time. The most standard, like the earliest method for this is Euler's method. Here are the equations for it. Here's like a 1D example of position and momentum and what happens when you use Euler's method for it. You can see that it's not, the gray line is the actual function. You can see that it's not following the function. It's not, and basically Euler's method is not volume preserving. Excuse me. And then what you can do is you can do a modified Euler's method where essentially you calculate the momentum first, and then you can calculate the new position. And that's, if you look to the right, this is what that looks like. And so this is a volume preserving method. But you can see that there's still some errors. And lastly, there's this thing called the leapfrog method, which is a 3-step process, or maybe you can say you have to perform 3 calculations. And this method is volume preserving and reversible. I'm not going to go into why, but it's in the paper. But so the reason why I'm saying this is I'm trying to give you all of the tools if you wanted to do Hamiltonian. Wanted to get good results. So I've talked about the Hamiltonian and the equations, but I haven't really said how we can apply it to MCMC, because MCMC is not like some object rolling around on the surface with kinetic energy. Like, what kinetic energy does a probability distribution have? And so how do you apply the Hamiltonian to MCMC? So what you do is I hope this chart is a little bit helpful. You have Q, which is samples from your target distribution. So Q is samples from the distribution you actually want to get samples from. And so you set that as your position variable. And then P are samples from another distribution independent of Q. So your momentum is from another distribution that's independent of Q. And then like the height, the thing that determines like the height, which determines your potential energy, is the unnormalized negative log likelihood function of the target distribution. So it's negative log of the target distribution's likelihood function. So that's how this is how they take this physics problem and make it into MCMC. They say, okay, Q is the samples are the samples I want to get. That's my target distribution. P is some other distribution, and height is this unnormalized, not negative log likelihood. How much time do we have? 4 minutes. Shoot. Okay, let's see what I can do. And so there's another step, which is they take an equation from statistical mechanics, which relates like the energy of a system to, or like its state. And this is called like the canonical distribution, where T is some temperature, Z is your normalizing constant, and E is your energy of your system. So they take this equation and they say, okay, my state is Q and P. If we look at the second equation, everything else is the same. And my energy equation is a Hamiltonian, because as we know, the Hamiltonian describes the kinetic energy plus the potential energy. But what's great about the Hamiltonian is that you can actually, because of what it is, which if we go all the way back up here, this, see, it's a sum of these two. And because of what it is, you can actually separate it out into the potential energy and the kinetic energy. And that's a really important element of the system, because what it means is, like, first off, you know that because these are independent, that P and Q are independent. But also it means that you have control over the distribution of Q by setting U correctly. So U is the potential energy, and what you can do is you can take this energy equation and you can take the original like statistical mechanical equation, reverse it, and you'll get like your energy equation should be equal to this. And we can ignore this constant Z. So that's how you get like U of Q is equal to this, of the negative log likelihood of the probability distribution. And so when you're choosing U and K, usually what they do is, this is like a Bayesian example where you have it's the negative log of the likelihood of Q given your data, essentially. And then P is, they usually use some equation like this, where your momentum is drawn from a zero mean Gaussian distribution with variance M, or M is some vector. So it's like a Gaussian that has a multivariate Gaussian that has a diagonal matrix with different values on the diagonal based on different dimensions. But the key thing is that these two are independent, so P doesn't depend on Q. Okay, I think I have like 2 more. Are you guys okay with going like 5 minutes over? If not, we can stop here and pick it up later.
Yeah.
Yeah, okay, cool. Okay, so what are the steps in Hamiltonian Monte Carlo? So when you're performing this algorithm, what are you doing? So you randomly sample a momentum P from the Gaussian distribution you have chosen. So like I said, P is some multivariate Gaussian with a zero mean. You randomly sample P. Then you use the current state Q and P. So Q from the previous state, the sample from the previous state, and P, to simulate the Hamiltonian for L steps using step size E by the leapfrog method. So maybe you do like 25 steps of the leapfrog method. Then you take P at the end of the simulation and you negate it. And this is important for the Metropolis proposal to be symmetrical, or basically for this to become reversible. So if we go back here, that's why I created this diagram. So basically, you sample a new P naught, and then you use the Hamiltonian equations to go from like Q naught to Q1 and P1. But then there's this extra step where you negate it, so that if you were to perform the exact same operations again, you would get back to the original state. So this step of multiplying by -1 is what makes it reversible, which is important. This is important to satisfy the detailed balance condition. Yes. And then you use the acceptance probability. This is the acceptance probability that you use to accept the new point, which is the difference between the Hamiltonians. We could look to the right part of the equation, but you see it's like min of 1 or the difference between the Hamiltonians times some exponential. Yeah, I explained why that's important. So one key insight that we might talk about next time is that exploration in Metropolis Hastings happens by sampling a new position. So in Metropolis Hastings, you're always sampling new positions to explore the state space. But exploration in Hamiltonian Monte Carlo happens by sampling new momentums. So you're using the momentum and a new momentum to change where you're going. Okay, yeah, this is the last slide. So how does Hamiltonian Monte Carlo meet the detailed balance condition? Because if it meets the detailed balance condition with the equation that we just described, then it is a valid way to perform Markov chain Monte Carlo. So I know I've really gone quickly through all of the steps, like basically all the setup to create this. But here's the detailed balance condition that we were just talking about. We've talked about quite a few times. And so you have this is your stationary distribution P, and then T is your transition matrix or transition distribution because, yeah. And so if you look back at our equations, like the ones we were talking about, then your stationary distribution is equal to this, where this V, by the way, it's never defined anywhere, but if you look in the paper, I'm pretty sure it's like the normalizing constant that we were talking about before for F, when we talked about F before. But anyway, so P of A is equal to this, and then your transition is equal to this. And then it's equal, the other side of the equation is like your stationary distribution is this, and your transition is equal to this. So these mins are the acceptance probabilities, and they define your transition. And as we said before, it's the difference of the Hamiltonians. And these two things are always equal. I just want to run through the why they're always equal real quick, and then we'll be done. So say that the minimum of these two is 1 on the left side. That means that the minimum on the other side has to be equal to, since this, if you look within the exponential on the left, it's equal to what's in the exponential on the right times -1. So if the left side's min is 1, the right side's min has to be the other component. And then if you just multiply the two exponentials on the right, you get what would be remaining on the left. And you could do the same thing vice versa. So if you look at it if you try out the two conditions, which is like when the left side is 1 versus when the right side is 1, they're always equal. These equations are always equal to each other, which means the way that everything is formulated, you meet the detailed balance condition. And so that's why Hamiltonian Monte Carlo can work. It's funny, everything, that's why I'm saying everything drops out from the detailed balance condition, because basically everything's formulated so that's true, because you know if that's true, that you've created something that converges to the correct stationary distribution. But anyway, yeah, that's the first part of Hamiltonian Monte Carlo. Thanks for staying some extra time. And I can stay for some more time too if anyone has any questions.
That was really good. Thank you.
Yeah, very great.
Thank you, Peter.
Thanks, Peter.
Okay, cool. I guess no more questions, but yeah, thanks everyone for coming. Really appreciate it. And feel free to give me feedback on this approach to Paper Club, where we're taking a very deep dive into math with respect to what we usually do. Yeah, everyone have a good weekend.
You too. Thank you.
Thanks. Bye-bye.
Thanks. Bye. Bye-bye.